Let's talk about underground fire protection piping, and more specifically, the approved piping materials. Understanding which materials are approved is crucial because it sets the foundation for a system that is both durable and compliant with codes and standards. When we choose the right materials, we're ensuring the longevity and reliability of the fire main system. This is a key step in the overall design and installation process, as it directly impacts safety and maintenance down the line. So, getting familiar with these approved materials helps us build a robust system that will perform effectively when it's most needed. Let's take a closer look at the general requirements and specific standards for underground piping. First, for any underground pipe to be approved for use, it must meet one of two key criteria. Either it must be specifically listed for fire protection service, or it needs to comply with recognized standards from organizations like the American Water Works Association, or AWWA, or ASTM International. This is important because it ensures that the materials used are suitable for their intended purpose and meet rigorous safety and performance standards. Now, this approach explicitly allows for a variety of materials, including cross-linked polyethylene, CPVC, and fiberglass, giving us flexibility in choosing the right pipe for different situations. Moving on to standards, we have a table that highlights some typical materials and their key standards. For example, ductile iron pipe must meet AWWA C104, which covers cement mortar lining, fittings, joints, coatings, and encasement. For concrete pipes, standards like AWWA C300, C301, C302, and C303 cover various types of reinforced and prestressed concrete pressure pipes. Plastic pipes, such as PVC and PE, are covered under standards like AWWA C900 and C906, which specify requirements for different sizes and materials. And for copper, standards like ASTM B75, B88, and B251 address seamless copper tubes and the requirements for wrought copper alloys. Overall, understanding these standards helps us ensure that the pipes we select are reliable, safe, and compliant with industry regulations. Let's talk about some restrictions on piping materials. First, steel pipe prohibition. Steel piping should generally not be used underground unless it's specifically listed for that purpose. The reason for this is that steel has a high potential for failure due to corrosion. Coatings and galvanizing can easily be compromised when placed underground, which makes steel less reliable in those conditions. Now, there is an exception for the fire department connection, or FDC. Steel piping is permitted only between the check valve and the hose coupling. This section must be externally coated or wrapped and internally galvanized to provide extra protection. The reason we allow this is because the FDC is an auxiliary water supply, not the primary one, so its reliability in this limited use is acceptable. Moving on to non-metallic pipes, like plastic. These are more vulnerable, especially where the pipe transitions above ground. They can be sensitive to fire and chemical spills, which can cause damage or failure. To address this, the pipe must transition to a more robust, durable material once it goes above ground, ensuring the system remains reliable and safe. Understanding these restrictions helps us ensure that our piping systems remain durable and effective under various conditions. Let's talk about some key design factors that influence our pipe selection and installation. First, fire resistance is crucial. This refers to the pipe's ability to withstand exposure to fire without failing. It's an important safety consideration, especially in critical infrastructure. Next, working pressure is fundamental. We need to ensure the pipe can handle the maximum pressure it will face in the system. The minimum rating allowed is 150 psi, or about 10.4 bar, but depending on local regulations, higher ratings might be necessary. It's essential that all components are rated for the system's maximum working pressure to ensure safety and durability. Another factor is installation depth. The depth at which we bury the pipe affects both protection and accessibility. Soil conditions also play a big role. They impact corrosion risk and soil stability. Knowing what kind of soil we're working with helps us choose the right materials and installation techniques. External loads are another consideration. These include weight from earth, traffic, or nearby structures. They can exert significant pressure on the pipe, so we need to account for that in our design. Now, moving to pipe linings, any ferrous metal pipe, like iron or steel, must be lined. This lining prevents internal rusting or tuberculation, which can severely reduce flow capacity and cause corrosion issues over time. When performing hydraulic calculations, always use the actual internal diameter, or ID, of the pipe, since the lining can affect the flow characteristics. Connecting all these points, understanding these design factors, helps us ensure that the pipe system will be safe, reliable, and long-lasting, fitting seamlessly into the overall infrastructure project. Now, let's take a look at fittings and joining methods. First, it's important to remember that fittings must meet either ASME or ASTM standards to ensure quality and safety. There are also special listed fittings, such as those made from CPVC, which are permitted under certain conditions. When it comes to joints and pressure ratings, they need to be compatible with the pipe itself, and the pressure rating should never be less than 150 psi or 10 bar to ensure the system can handle the required pressure. Moving on to joint protection, it's crucial that joints are assembled by trained personnel to guarantee proper installation. Additionally, all bolted accessories should be cleaned and coated with a corrosion-retarding material after they are installed, which helps prolong the system's lifespan. Now, let's talk about some common types of joints. Push-on joints are typically used with ductile iron and PVC pipes. They feature bell and spigot ends along with rubber gaskets to create a secure seal. Threaded joints are used with steel pipes, and it's vital that the threads meet the ASME B121 standards for safety and reliability. Grooved joints require a listed combination of fittings, gaskets, and grooves to ensure a proper fit. Finally, for copper pipes, brazed or pressure joints are the go-to method. These methods provide a strong, leak-proof connection, which is essential for maintaining the integrity of the system. Throughout all these methods, the key is selecting the right fitting and joint type for the specific pipe material and application, always prioritizing safety and durability. Let's talk about the depth of cover and freezing protection for our pipes. Proper burial depth is really essential to protect pipes from freezing, especially in colder climates, and also to prevent damage from surface loads like traffic or equipment. It's important to remember that private fire mains, which usually have static water, need a greater cover than public mains. This added depth helps ensure the water inside stays unfrozen and the pipes remain protected. Now, looking at the minimum burial depths. In frost protection areas, pipes should be buried at least 1 foot or 0.3 meters below the frost line to prevent freezing. In non-frost areas, a minimum of 2.5 feet or 0.8 meters is recommended. When pipes are installed under driveways, where there's more traffic and weight, a minimum of 3 feet or 0.9 meters is advised to prevent crushing or damage. And under railroad tracks, because of the heavy loads and vibrations, at least 4 feet or 1.2 meters of cover is necessary. These guidelines are all about ensuring durability and safety for the piping system over its lifespan. Proper burial depth is a key part of protecting our infrastructure from environmental and mechanical stresses. Let's discuss some important considerations for protecting piping and electrical systems from damage and hazards. First, when it comes to piping under buildings, the general rule is that pipes should not be run beneath structures. The reason for this is that repairs can become extremely difficult, and any leaks could potentially undermine the building's foundation, leading to serious issues. However, if running piping under a building is unavoidable, there are special precautions that need to be taken. These might include arching the foundation or installing the pipe in covered trenches to protect it from damage. Also, it's important to remember that pipe joints should never be located under foundation footings, as this can compromise the stability. Now, shifting to electrical considerations, one key point is about dissimilar metals. Whenever pipes join different types of metals, those joints must be electrically insulated to prevent corrosion and electrical problems. Speaking of grounding, piping should never be used as a grounding electrode for electrical systems. Using pipes as ground can lead to corrosion and safety issues. Finally, in terms of bonding, pipes must be bonded to the lightning protection system, following NFPA 780 standards. This creates a common ground potential, which helps protect the system and personnel from lightning strikes or electrical faults. Overall, these measures are crucial for maintaining safety and integrity in our infrastructure, aligning with the broader goal of ensuring reliable and hazard-free operations. When it comes to installation, handling, and support, I want to emphasize some key points to keep in mind. First, always inspect all materials carefully when you receive them and again before installation. Look for any damage that might have occurred during transit. Making sure everything is in good condition helps prevent future issues. Next, ensure the interiors are clean before you install anything, and if you need to pause work, plug open ends to keep debris out. It's also very important to handle water main materials with care. Never drop or dump them. Lowering all materials carefully into the trench prevents damage and ensures safety. Now, talking about proper support, this is absolutely critical. Pipes need to be supported along their entire length. Supporting only at the bell ends or on blocks isn't sufficient because it can cause stress and potential failure. If you're working in soft ground or quicksand, make sure you make special provisions for support. Extra precautions are necessary in those conditions. For non-metallic pipes, support valves and fittings as specified by the manufacturer. Proper support isn't just about following rules, it's about ensuring the integrity and longevity of the system you're installing. Overall, these practices are essential to a successful installation and to maintaining the system's durability over time. Now, let's discuss joint restraint methods, which are crucial to ensuring the integrity of the piping system. Any component that creates thrust forces, such as T's, bends, valves, and plugs, must be properly restrained against movement. This is important because without restraint, these joints could separate under pressure, leading to leaks or failure. One common method is using thrust blocks. These are concrete blocks placed between the fitting and the undisturbed earth. They work by transferring the thrust force to the soil, which must be capable of bearing the load over a large area. It's also important to position these thrust blocks so that joints remain accessible for future repairs or maintenance. The other main method involves restrained joints, which are specially designed to handle longitudinal forces. Examples include locking mechanical joints, bolted flange joints, pipe clamps, and tie rods. Whenever metal restraining components are installed, they must be cleaned and coated with a corrosion-retarding material. This helps ensure long-term durability and prevents corrosion from compromising the restraint system. Together, these methods help us control thrust forces effectively, maintaining the safety and reliability of the entire piping network. Now, let's talk about backfilling and final acceptance. When it comes to backfilling requirements, it's important to tamp the backfill in layers. This helps prevent settlement over time, which could compromise the integrity of the installation. Remember, you should avoid using ashes, cinders, refuse, rocks, or any corrosive materials for backfilling, as these can cause issues down the line. For trenches that cut through rock, make sure to use at least 6 inches of tamped backfill around the pipe as a cushion. This provides extra support and protection for the pipe in challenging conditions. Moving on to contractor responsibilities, as outlined in Section 10.10.1, it's crucial to notify the authorities and the owner before testing begins. This ensures everyone is aware and prepared for the inspection process. You are also responsible for performing all the required acceptance tests, which verify that everything meets the project standards. Finally, after completing the testing, you need to complete and sign the contractor's material and test certificate. This document officially confirms that all work has been done according to specifications and that the system is ready for final approval. These steps are essential to ensure the project's quality, safety, and compliance, tying everything together in our overall theme of thorough and responsible construction practices. Now let's talk about acceptance test 1, which focuses on flushing the system, specifically at point 10-10-21. Before we connect the underground piping to the rest of the system, it's essential to thoroughly flush it. The main goal here is to remove any foreign materials that might have entered during installation or storage, things like stones, tools, or debris that could cause issues later on. When we're flushing, one key aspect to keep in mind is the required flow rate. It's not just about high volume, it's about achieving the right flow to ensure the piping is properly cleaned. The flow rate needs to be the greatest of three things: the system's hydraulic demand, the maximum flow available, or a flow rate that results in at least 10 feet per second velocity within the pipe. Looking at the table, for example, if you have a 4-inch pipe, you need a flow rate of around 390 gallons per minute to reach that 10 feet per second velocity. As pipe sizes increase, the required flow rate also increases significantly, up to 3,520 gallons per minute for a 12-inch pipe. This ensures that the flushing is effective regardless of pipe size. In summary, the most important points are to make sure the piping is thoroughly flushed before connection, and that the flow rate used is sufficient, either matching the hydraulic demand, the maximum flow available, or achieving that 10 feet per second velocity. This step is crucial for maintaining system integrity and preventing future issues. Now, let's talk about acceptance test 2, which is the hydrostatic test. When conducting this test, we need to apply a test pressure that is either 200 psi, or 13.8 bar, or 50 psi, or 3.5 bar, whichever is greater. This ensures we're testing at a pressure that exceeds the maximum working pressure to verify the integrity of the system. We then need to maintain this pressure for a duration of 2 hours. During this time, it's important to monitor the pressure readings carefully. Always read the pressure from a gauge placed at the lowest elevation point of the system, so you get the most accurate measurement of any potential drops or leaks. Speaking of leaks, there is a leakage allowance to consider. Before testing, the trench must be backfilled between joints. This helps prevent unnecessary movement or disturbance during the test. Also, a small, calculated amount of makeup water is permitted to account for minor leakage that might occur over the 2 hours. Remember, if there's excessive leakage, it's the contractor's responsibility to address and fix it. This test is crucial because it confirms the system's ability to hold pressure and operate safely under expected conditions, tying back into our overall goal of ensuring system reliability and safety. Now, let's talk about acceptance test 3, the operating test. Once we've completed flushing and pressure testing, it's crucial to verify that all system components are functioning correctly under pressure. This step helps us ensure the entire system operates as intended. First, we'll focus on hydrant operation. Each hydrant must be fully opened and then closed to check for proper functionality. For dry barrel hydrants, we also need to confirm proper drainage, so no water remains trapped inside. Next, we move to control valve operation. It's important to fully open and close all control valves while the system is under pressure. This process confirms that the valves respond correctly and can handle real operational demands. Finally, if your system includes fire pumps and backflow preventers, these components need special attention. Pumps should be tested while running to observe their performance under actual operating conditions. Similarly, backflow preventers must be tested at the system demand rate to ensure they prevent reverse flow effectively. All these steps are vital because they mimic real-world scenarios, and verifying these functions ensures the system's reliability when it's truly needed. Remember, thorough testing now helps prevent issues during an emergency, keeping everyone safe. Thank you all for being here today. I really appreciate your time and attention throughout this presentation. If you found this information valuable, I encourage you to subscribe for more updates and insights. Your support helps us continue to share useful content and stay connected. Remember, staying engaged and informed is key to making the most of what we've discussed. So, once again, thank you so much. And don't forget to subscribe.